I'm going to start talking now about very, very important stuff. We are saying a fresh marker, and we're going to continue our conversation about combinatorics today. So, started this the other day, but we need to talk about this stuff. So here we go. We are ready for problem number 3 on the very first page. And the question is, how many 9-letter words can be formed from the letters of dragonfly? So what that means is, if we took those letters, how many other ways could we arrange them? Well, how many of those letters are there? 9. And we talked last time, and I made a big deal about it, that 9 things in a row is 9 factorial. So if there are 9 letters and you are arranging them, it can be done 9 factorial ways. Now I want you to look at the next word, butterfly. How many letters are in that word? 9 factorial again, but there's something different about that word. What is different? There are repeated letters. Now, this is how you handle duplicates. The other day, we talked about distinguishable versus non-distinguishable things. T's are non-distinguishable. The first T looks just like the second T. All right, so here's how we handle that. There are 9 letters to be arranged. So we start with 9 factorial. I don't care that some of them are duplicated, doesn't matter. There are 9 letters. There are 2 T's, is that what we've got in this word? So I'm going to divide by 2 factorial. When you have duplicates, you divide by the number of duplicates factorial. Okay? And when I type this into my calculator, there is no shortcut. There's no canceling. You cannot do that. It's going to be 9, whatever 9 factorial is, divided by 2, which is 2 factorial. Okay? Now look at the next word. Bumblebee. How many letters are in that word? 9. So we're going to start with 9 factorial. But what? 3 of them are B's, so we divide by 3 factorial. That takes care of the B's. But then we also have to divide by
6.
No. Well, by 3 factorial, which happens to be 6. So I'm going to divide by another 3 factorial, which is the E's. So when we have duplications, we divide by each duplicate factorial. So 3 factorial takes care of the B's, 3 factorial takes care of the E's. When you type this into your calculator, let's all do it to make sure we get it right. Remember that when there's more than one number in your denominator, it's got to be in parentheses. Okay? Or the way I type these in, and again, do it however you want. But if you do it the way I wrote it, you got to have parentheses around this. I like to type it in 9 factorial divided by 3 factorial, and then I hit equals, and then divided by another 3 factorial. All right, 3 factorial is in your math menu. Or factorial, go to your math, go across the prob, and down to the factorial sign. The answer that you should get is 10,080. This should be 10,080. So as long as you're getting that, you're all good. All good. Now, when you found your factorial, did you notice that in that list where the factorial was, there was an N, P, R, and an NCR button, something like that? Is that what it looks like?
Yeah.
Did you notice that? Okay. So we're gonna be using those buttons a lot. Exercise number 4 says evaluate without a calculator, but before we do that, I want you to understand the difference between doing a P problem and a C problem. So would you turn to problem number 6 real quick? We're gonna come back and get the others. I just want you to know the difference between a combination. C is a combination, and P is a permutation. I want you to know the difference between those two. So I'd like you to read question 6. A and B. And tell me what the difference is between those two problems. 6A and B, what is the difference? Well, what's the same? They both involve a group of 20, and by choosing 3 out of there, right? Okay, so tell me what's the difference? They are different problems. What's the difference? Seth?
Would B be in any order and A be like each one?
Exactly. In A, when I pick you, what is this you're wearing? What is that? What are you wearing? A green shirt. Oh my gosh.
It's okay.
I'll just write it up again. What the heck, yeah. Okay.
6A, 6B.
In problem A, I'm not picking, if I pick you first, you are president, then you are vice president, and you are treasurer. But if I pick you first, you're president, you're vice president, you're treasurer. You see? But if I'm picking a leadership group, does it matter if I pick him first or last, if it's just a leadership team? No. When order matters, when your order of choice matters, it's a permutation. So to do problem A, I would set it up as 20P3. There are 20 to pick from, and I am picking 3, and the order I'm picking matters. So when I type this in on my calculator, I hit 20, then I go to where my factorial is, math, prob, only I don't pick the factorial, I pick the NPR button, and then hit 3, and it should give you the answer. Right? Which is what? 6,840. Now, the thing about P's is, they can be done the way we did our license plates the other day. In other words, if I am picking the president, vice president, and treasurer from my class of 20, how many choices do I have for president? No, how many choices do I have? 20. Then I pick somebody to be president, so now I have 19 and then 18. Well, go ahead and multiply 20 times 19 and 18, and you will get 6,840. So a permutation problem can be set up as a blank, because you're choosing an order, first, second, third. A combination problem, when I am choosing 3 and order doesn't matter, cannot be done that way. A combination problem is entered into the calculator as 20C3, and it will be less options. $1,160, is that right?
40.
40? Because my math in my head is very good. Okay? Now, what does, when you read a problem, and there'll be lots of them, and you have a group of stuff, and you're gonna pick a few out of there, it's always gonna be a P problem or a C problem. If you have a big group, and you're picking a few out, it's a P or a C. How are you gonna decide if you're doing a P or a C? Right there. You're gonna ask yourself, does it matter who gets picked first? If it matters, it's a P. Okay?
So you showed how you can do 20, 19 times 18 and stuff. How would you do that for C?
Can't do it. Can't do it that way. The minute you put blanks up here, you're putting order into the problem for second, third. So I'm going to give you the formulas that operate behind the scenes of the calculator. But I wanted you to see the distinction between the two first. Okay, you got it? Got the difference? All right. Now, Seth's question was, how do you calculate these things by hand? Well, a P, I'll just look at number 4A. Certainly I can type that into my calculator and get an answer. If I were doing it by hand, remember when Miss Ford was growing up, had to do all this by hand. I think you guys forget we did the very same math you're doing, but we did it without a calculator. So how did we do this? Well, the formula for P's for this one would be 6 factorial over 2 factorial. Now, where do you think the 6 came from?
6.
Right there. Where do you think the 2 came from? The difference. The difference. So in general, NPR is n factorial over n minus r factorial. That's how you can calculate a permutation if you can't use a calculator. Now, the nice thing about these is some things always cancel. You cannot cancel 2 into 6. That's not the way this works. But if you write out 6 factorial, do you see that that part will cancel? And so you would end up with 30 times 12, which is 360. Is that right? So the answer would be 360. Now, the reason we have to know the formula is for a problem like C. C cannot be typed into the calculator, problem C, 4C, because it has a variable in it. So what will the setup for NP3 be? NP3.
N minus 3.
N factorial on the top.
N minus 3.
And n minus 3 factorial on the bottom. Now, how does that simplify? Well, what does n factorial mean? N factorial.
N times n minus 1.
N times n minus 1, n minus 2, n minus 3, n minus 4, dot, 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 dot. Isn't that n factorial? So what is n minus 3 factorial? N minus 3, n minus 4, dot, 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 dot. Well, what happens?
They all cancel out.
Everything from here on is going to go away. And so your answer is right there. All right, make sure you know the formula for permutations. We're going to also learn the one for combinations. Okay? Now, for some reason I've got the combination problems later on, but we're just going to do it right now because it makes sense to do it right now. So we're going to do, let's say we had 6 C4s. We don't. Let's put this over to the side. I'm not. I'm freelancing, okay? I'm allowed. I gotta put her back to section 9 too for some reason. All right, so what's the formula, or how is the setup for 6 C4? Just stick this over the side, folks. Like, take an independent note here, over to the side. 6 C4 would be 6 factorial over 2 factorial, exactly like the permutations were, but there's an additional 4 factorial in the denominator of a combination problem. So, where did all these numbers come from? If the problem was 6C4, then we have 6 factorial on the top, we have the difference, and then we have that number also. Now these cancel a ton. Think about it. You have 6, 5, 4, 3, 2, 1 on the top. And on the bottom you have 2, 1, and 4, 3, 2, 1. You're gonna lose a lot. All that's gone. 2 goes into there. The answer to the problem is just 15. So your formula for combinations, your general like formula for combinations, would be n factorial over what? What am I going to put in the bottom? N minus r factorial, r factorial. Look, right here, kids. Look how we did it. 6 factorial, we subtracted, and then put that number down there too. That's your combination. This number, as long as you're picking more than one thing, this number will always be less than that number. Doesn't that make sense? If I'm picking things in order, there's more than if I'm picking them not in order. All right, let's see what's happening. Number 5. 16 actors answer a casting call for 7 different roles. How many ways can we fill the spots? All right, I want you to think about this in terms of what we've been discussing. How many people are in the room? 16. How many am I picking?
7.
It's always going to be either 16P7 or 16C7. You got to decide.
C.
P.
100%.
Going with Seth.
100 P.
Okay, why do you think it's a P?
Seth said so.
Seth, why do you think it's a P?
Because you can't have 2 people at the same part.
Well, you can't with a combination either.
We want order.
Wait, like,
Why do we want order?
Oh, you have to read the after.
Exactly. Thank you, Mary. It matters which role you give them.
Yep.
If he's playing King Lear, and she's playing, what's the daughter's name? One of the girls. Then that's different than if she's King Lear and he's one of the girls, right? I pick the same 2 people, but if I give them different roles, it's a different show. Different play, right? Order matters. Problem number 5 is 16P7. Now, back in the old days at Cathedral High School, the musical was a no-cut thing. Anybody who tried out for the musical could be in it. So the musical had like 300 people in it. But you don't have 300 roles in anything. So there were kids who played bushes and trees. Okay? So suppose that I got these 16 people and I'm going to pick 7 of them to be bushes. Very good. I'll pick you. That would be a C problem because the roles are all the same. If the roles are the same, the orders that I pick them don't matter. Everybody's going to be a bush. Instead of somebody's the king, somebody's the queen, somebody's the princess, right? That's different. That's a P. Got it? Yes. Okay, why's your hand up?
I have a question. What if it's like half of the roles are the same?
Then you have to split into 2 pots. It would be like a deck of cards. You got your jacks, you're picking from jacks over here, and you're picking from clubs or something over here. Bad analogy. Diamonds over here, clubs over here. Yeah. Then you have to split it up.
But if that's the same sample size, how would that work?
Doesn't have to be the same sample size. If I have 7 Republicans and 3 Democrats, and I'm gonna pick 2 of each, 7C2, 3C2. Think about that. Just think, maybe I'm misunderstanding. Let's get a little further into the conversation, okay? And let's not start overcomplicating things just yet. Number 7, how many ways can a cook, a reporter, and an announcer be chosen from our class of 25?
22,
25, P3. Why is it a P? It says 25. All right, number 7. Why is it a P?
Different jobs.
Different jobs. Different jobs. How many ways can a chef choose 5 potatoes from a bag of 12? 12C5. 12C5. How many ways can I make a seating chart for 22 students if my room has 30 desks?
22.
Yeah, I want to talk about that. I heard somebody say 22C30. Now let's talk about that for a second. Think about that for a minute. What does that say? That says I have 22 and I'm choosing 30. Is that possible?
No.
If you try to type that in on your calculator, it will tell you. It will say error. Now, it could be 30C22 or 30P22. What do you think? Does it matter where I sit you in a seating chart?
No.
Well, you can't.
You can't sit in the same spot. You're ridiculous.
Guys, stop. Stop.
P.
Common sense enters my brain. It is a different seating chart, a different seating arrangement. If I switch those 2 people around over there, that's a different seating arrangement, right? Order matters if you are arranging people in seats, or arranging people in a line, or arranging anything. Arrange means order, putting them in order. This problem is 30P22. 30P22. All right, how many ways can 10 finalists be chosen from a group of 51 contestants in a beauty pageant? Okay, so this is like Miss America. You ever watch Miss America? You got 51 people, you got all the states in the District of Columbia. And someplace along the way, they say, okay, we're gonna narrow it down to 10. And they start naming the 10 people. Okay, so is that gonna be 51 P10 or 51 C10? C. You don't care if you're named first, second, or third, or last, you just wanna get named, right? You wanna be in the finalist pool. So that is 51C10. All right, a lottery requires you to pick 6 integers from 1 to 46. How many different lottery tickets are possible?
46.
I heard a 46P6, and I've heard a 46C6. What do you think? If your life depended on it, what would you say? C. When they draw lottery tickets, isn't it the numbers that matter? The numbers don't have to be in a particular order. No, they don't. Who's your lottery? They pull it. No, you have to have a Powerball in a specific spot. That one is special. But the other ones, they just draw those out and they can be anywhere. But yes, the Powerball is a separate thing, and that would be a different question. Yeah. All right, a pizza shop offers up to 10 toppings. How many different pizzas are possible if we can choose any 3 toppings? So you walk into your pizza shop, you're going to pick 3 toppings off the menu. 10C3? Now, some of you might be pizza connoisseurs.
Yep.
And you might say, oh, no, my pepperoni has to go on before my sausage goes on, or whatever, okay? But that's just weird. We're just picking 3 toppings, it's gonna be 10C3. Now, whoa. What if we can choose any number of toppings, including none?
Obviously.
Okay. So what this means is, let's think about it. We're gonna discover something here in a minute. Let's think about this for a minute. That means, including none, that means 10C0, right? There's 10 toppings, but I'm not ordering any of them. Or 10C1, or 10C2, or all the way up to 10C10. Isn't that what this problem is saying? Okay, so here's what I need you to do. We're gonna split up in groups, because this is a bunch of numbers. Let's have you guys here. I want you to find these first three for me. Find these first three numbers. You guys are gonna do 10C3 through 10C7. And then you guys are gonna do 10C8 through 10C10, all right? So find those numbers for me on your calculator. 10, math, Bob, NCR 0. 10, math, prob, so on, so on, so
This is
on.
10. Is 10C2 is 2?
I got 1.
I got 10.
I got
I got
1.
1.
Okay, 10C0 is 1, I know that. 10C1 is 10.
10C2 is like 100?
No.
45.
No. 10C2 would be 45.
What would you even say?
All right, so you guys are out.
120.
120. 4.
2.
This is what.
10.
This is what.
5.
She just goes over to math. She goes to math, prob, and then she goes.
52.
One day she's just like,
Let's see, how about 7? 10C7. Wait, I missed one. This is 3, 4, 5. What's 10C6?
2 times.
I counted wrong here, but you guys, okay. And then you got 120. And you guys should have gotten 45, 10, and 1. You guys should have gotten 45, 10, and 1. All right. So in this problem, we ultimately needed all of the combination numbers for 10. 10C0, 10C1, 10C2, all the possible combinations. So we just calculated that on our calculator, and these are the numbers that came out. Now I want you to think about this. Megan noticed, she said, well look, it just repeats on the other side. I want you to think about that for a second. This number right here is 10C2. This number right here is 10C8. Now think about this for a second. You see where I'm going with this, Seth? There are 10 people in the room. If I say, all right, I'm going to take these 2 on a camping trip. So I have picked these 2 out of my 10. The act of picking 2 has automatically picked the other 8. I have 2 chosen and 8 unchosen. Those are exactly the same number, because when I take you 2 out of the room, the other 8 of you are left here. If I take 8 of you out of the room, the other 2 of you are stuck here. So that means, I'm not surprised at all, that 10C3 is the same as 10C7. Do you see what I'm saying? Makes perfectly good sense. All right? Now what I want you to do is take your, so this thing is symmetrical. It's symmetrical. I want you to add these numbers up for me. Add these numbers up, all these right here. You are not going to get a random sum. You are going to get a very meaningful sum.
You can do that times
1024.
That's what I got, yeah.
I want you to type 2 to the 10th power on your calculator.
No, I didn't know there was 10, 24, 21.
Oh, all right.
Such a small.
So the sum of the numbers in the 10th row, or in the combination 10 row here, the sum of those is 1024, which is 2 to the 10. So what if the pizza shop had 11 toppings? Then these would be 11C0, 11C1, 11C2, and so on. What would they add up to? 2 to the 11th, right? So if you need all the combination numbers for a certain number, in our case 10, it's always going to be 2 to that power, whatever it is. Okay? So read the next question. So the answer to question number B, the answer is 1024.
You know why it's like that?
Yes, we'll talk about it. Number 13. A hamburger chain once advertised its six burgers 256 ways. How many toppings must have been available? So if all of the options added up to 256, then how many options must there have been? How many toppings must there have been? Huh? No. No.
First 7 to 0.
2 to what power is 256? So there must have been 8 toppings possible for all of the options, boys, for all of the options to have added up to 256. Kids, back up. Remember, we actually worked this out. We had 10 toppings and it added up to 1024, which is 2 to the 10. So if we know we have a total of 256, then we got to figure out 2 to what power will give me that. And you said 8. So there are 8 toppings possible. I promise we're going to spend more time. That's really a 9.2 question that you asked Seth, so I promise we'll come back to it. But big observations that we've made so far. We have a lot to do. Big observations. The difference between P and C. How to calculate them by hand in case they have variables in them instead of numbers, right? The fact that if you have a set number of options and you are going to choose all the possible combinations of those options, it's always going to add up to 2 to however many options you've got, right? The fact that I'm highlighting some of the important points. The combination numbers are symmetric. So I know automatically that 9C5 is going to be exactly the same as 9C4 every time. Those are going to match. Okay. All right. Here we go. Number 14. How many different 5-card hands are in a standard deck? How many cards in the deck? 52. How many are we picking? 5. In the order we pick them doesn't matter. We are not talking about specific games. We're not talking about having to have cards in a certain order. We just want to know how many hands are possible. There it is. How many have all red cards? No, not half of that. Because what you're saying, Jake, stop and think about what you're saying. Stop. If I deal everybody in this room a 5-card hand, will half of the hands, half of you have all black and half of you have all red?
There's 52 people.
Are you serious? Are you joking? They have 5-card hands, not one.
So you could have, probably if I dealt him a hand, he would get maybe 2 reds and 3 blacks, okay? And you might get 4 reds and 1 black, and he might get all 5 blacks maybe, right? So no, it's not half. Now, what is half? What is half is the number of options I have to pick from. If I must have an all-red hand, then I only have 26 cards to pick from. This is not half of this. Okay, I promise. You can type down the calculator, okay? Now, how many have at least 3 red? Now, that means you have 3 red, or 4 red, or 5 red. Would you agree with me? All right, how many 5-card hands have 3 red?
26, C3, 26, C4, 26.
Okay, now, we're not done, but is that an okay way to start? With this giving 3 red cards? Yes, but it's a 5-card hand. So if 3 of them are red, then 2 of them have to be black. So 3 red and 2 black. Or 4 red and 1 black. Or all 5 red. Does that make sense to you? Remember, it's a 5-card hand. So if exactly 3 of them are red, then the other 2 have to be black. You can type this in without writing anything down. Just type 26 C 3 times 26 C 2 plus 26 C 4
Drink your OJ.
and so on.
Still a page left in there.
All right, see if this is what you got. Sometimes when I'm talking, it's not a mistake.
That's what I got.
So I'm discouraging you from doing each step individually and writing it down. It just takes too much time. Your calculator can handle that. Just type it all in. All right. How many 5-card hands have all diamonds? 13 C5. Why? Because there are 13 diamonds in the deck. So there's 13 cards to pick from, and you're going to pick 5. Have 2 diamonds and 3 clubs. 2 diamonds and 3 clubs. Isn't that it right there? 2 out of the diamond pile and multiply 3 out of the club piles. Have no cards higher than a jack, and aces are considered high in this problem. Okay, so what can I not have? I cannot have a queen, king, or an ace, right? So how many cards am I taking out? I'm taking out all the queens, kings, and aces. I'm taking out 12, so I have 40 left. So the answer is 40 C5. So 52 cards, I'm taking out 4 aces, 4 kings, 4 queens. That leaves me with 40 cards. How many 5-card hands have the king and queen of spades? Now wait a second. How many queens of spades are there in the deck? 1. 1 C1. There you go. You got your queen of spades. How many kings of spades are there? 1. There's 1 C1. You got him. All right. So we now have picked our queen, and we've picked our queen. Now what else do we have to do? I have to pick 3 more cards. And where are those 3 coming from? Not the queen of spades and not the king of spades, right? So 50,
C3.
So embarrassing.
2 minus 6.
Okay? You everybody got it? All right, I've got 10 juniors, 8 seniors. How many ways can I pick 4 and get all juniors? I heard somebody say it. 10C4. There are 10 juniors. I'm picking 4 of them. 10C4. Easy. Get 2 of each.
Whoa.
10C2 times 8C2. 2 from the junior pile and 2 from the senior pile. I need to get more seniors than juniors. All right, I need to get more seniors than juniors. Now, wait a minute, I'm picking 4 people. If I have to get more seniors, then don't I need 3 seniors or 4 seniors? So what does 3 seniors look like?
3C8.
8C3 times 10C1. Remember, I'm picking 4. If 3 of them are seniors, one's got to be a junior. Agreed? Or I can get all seniors. Okay, we gotta finish this page, so I need everybody paying close attention. How can I make sure that Tommy is on the team? 1C1, right there's Tommy. 1C1. And then how many more people do I need to pick? How many people do I need to pick? 3. Do I care what they are? No. How many people are left if I pull Tommy out? I don't care if he's a junior or a senior. How many people are left? 17. So 17. Here's Tommy. There's 1 Tommy, and I picked him. Now, there's 17 people left, and I'm going to pick any 3 of them. Right? Make sure that Tommy is not on the team. Seth says 17C4. I hear a no.
That could be anyone. Tommy would be
Because I did it.
Okay, so here we are in a room. Here, let's say there's 18 in the room. All right, 18. I'm going to pick 4 people. I do not want Tommy. Don't tell him. I do not want him. So here's Tommy right here. So I put him out in the hallway. I don't want to pick him, so he's out in the hallway. How many people are left in the room? How many am I picking? I think he's right. Seth is right. 17.
Who was that one, Seth?
All right.
Who was everyone? No.
We got to get through this problem, and there are some weird things going on. All right. How many ways can I arrange 3 of these identical twig books, 4 different geometry books, and 5 different algebra books on the shelf? Now, here's what I want you to think about. I want you to think about these books as being letters. Remember the words we did at the very beginning of the period, bumblebee and all that? So these books are like letters. Each book is a letter, but some of the letters are the same. Right? So what do you think is the setup for problem A? All right, so you say 12 factorial over, what did you say? 3, 4, and 5? All right, let's talk about this. I don't think this is right. But
Straight on his
so
top.
mean.
No, I love that. They're not like besties, but like.
All right, I believe the 12 factorial is correct. Because how many books are there? 12. And when there's 12 books, they can be arranged 12 factorial ways. Dylan? Yeah, so they're like different letters, right?
Go for it.
So what do I need to divide by? Just the 3 factorial? Kids, please keep in the back of your mind that because things are in the same category does not make them identical. Think of boys and girls, right? You're not identical, you're different. Well, these books are different. These books are different, so they're not divided. Okay, so everything's the same in problem A, except the books of each kind must be kept together. So in other words, instead of just putting them on there, I gotta have all my trig books together and all my algebra books together, all right? This is what we call bundling. Because basically what I'm doing is bundling my algebra books and saying, okay, you guys have to stay together on the shelf. And you guys stay together on the shelf, okay? How many things am I really arranging then? I'm only arranging 3 things. You get it? There's 3 bundles. Tie a string around them. You can't separate your algebra books. There's a string around them. Trig books, geometry books. So there's only 3 bundles to arrange. So we start with 3 factorial. But I want you to think about this. When I tied a string around my geometry books, there were 4 of them. Could that little bundle itself be rearranged? And since there are 4 of them, it could be rearranged 4 factorial ways. So this 3 is the bundle. This is my geo base. Well, similarly, I can do 5 factorial for my algebra books, right? Now, technically, I should also do 3 factorial for my trig books. But what am I going to turn around and do? Divide by 3 factorial because those books are identical. So there's no real way to rearrange those books. They look exactly the same. So this is going to cancel, and that's going to be the answer to the problem. How many ways can I arrange 14 students in a circle? Does a circle change anything? Let's think about that for a minute. Let's say you guys are in a circle here. Pretend you 4 are in a circle. Okay? Now, if I tell each one of you to go 1 seat this way, okay? So here we lose over here, and you move back there, and over there like that. Is that a different arrangement?
Nah.
No, they're sitting in different seats, but it's not a different arrangement. Because circles have no beginnings and no ends. Now, if I took these 4 right here, and I said, okay, everybody shift over 1. So you got up and went down there, and everybody shifted down. That's a different arrangement. Because now, Allie's on that end, and that's different than when Fisher was on that end. When things are arranged linearly, if there are 14 of them, it's 14 factorial. But when they are arranged in a circle, it's 1 less factorial. Because you 4 of those patterns are exactly the same. There's rotations of each other. So, how many ways can 14 people be arranged in a circle? 13 factorial. 13 factorial. When you arrange things in a circle, it is 1 less factorial. How many ways can I seat 5 people around a campfire? 4 factorial. How many ways can I seat 5 people on a log? 5 factorial. Right. A line is n, a circle is n minus 1 factorial. Perfect. 6 different, how many ways can I arrange 6 different beads on a bracelet with no clasp? So do we know what we're talking about? Anybody have a bracelet on with a bead? Okay, so one of those little stretchy things you put over your hand How many ways can I arrange those beats? 5 factorial. Oh, but wait. There's more. Do we get why it's 5 factorial? It's a circle, an unbroken circle. 5 factorial. But here is the tricky thing about what are called handheld circular permutations. Remember, the question is how many ways can I arrange these beads? That means physically change their arrangement. So let's say I have this bracelet and I have my pink bead and my green bead and my blue bead and my yellow bead. How many were there? 6? Orange and lilac. Okay? So here's my bracelet. Got it? Now, let's say I have this bracelet in my hand right here. This is what it was. Here's purple and green and black and all everything. There it is, right? What if I took that bracelet that's laying right there in my hand and I went like this with it? Now I'm looking at it.
Like mirrored.
Exactly. And I can't count that mirrored thing would be, this is not a different arrangement. Now, if it's people, if these are people, that's a different arrangement because they moved. But if all I did was take my handheld thing, my bracelet, and turned it over, it looks different, but isn't it exactly the same thing? That's called a reflection. And so what you have to do is, you have to take your 5 factorial and divide it by 2. Because only half, if you were to draw everything on the blackboard, only half of those would be actual new patterns. The other half would just be reflections of what you had originally. We do not reflect everything. We reflect handheld circular permutations. So if it's a circle that you can hold in your hand, necklace, bracelet, keychain, that's about it. You need to divide by 2 to take care of the reflections. Alana?
So for like these kind of questions, why are we using like the factorial thing instead of like the C and D?
Well, because these are, well, first of all, when you arrange in a circle, then it's a whole different ballgame. But we're not choosing from a pile. I'm saying I have 6 beads, how many necklaces can I make? Right? We use P's and C's when we have a big group, and we're picking a few out of the group. Not doing that here. All right, letter E. Okay, so this is the answer. This is the answer to letter B. All right, letter E. How many ways can I arrange 6 different beads on a bracelet with a clasp? 6 factorial over 2. That's the answer to E. Now, Mary, tell me why it's 6 factorial.
Since there's a clasp, it's like they're in a row because it's not like a full circle.
You all know what a clasp is on a necklace?
Tell you we can't
Okay,
get through it.
so what do you do? What does a clasp do? It turns that circle into a line. It breaks the circle. So when you have a clasp, it reverts back to the linear. It's a line. You're still divided by 2 because you can still reflect it, but it's a line. Right? You can't get it off without opening it up, right? All right, last one, and this one's a doozy. How many ways can I arrange 4 couples in a row at the movie theater if each couple has to sit together? All right, I heard a 4 factorial. So let's talk about that. Who said 4 factorial? I heard that. Megan, you said 4 factorial? Okay, what? What a cop out.
I get right.
Colin.
Would it be like the bundle of books and it'd be 4 factorial, 2 factorial?
And then 2 factorial, 2 factorial, 2 factorial, because here are, okay, so here are our couples right here, okay? So we're all going to the movie theater, and you guys gotta sit together, or they gotta sit together, and you guys and you guys. So basically what I'm doing is like tying you together, okay? So when I walk into the movie theater, I sit bundle 1 here and bundle 2 here and so on. There's 4 of these bundles, so that's 4 factorial. Megan was exactly right. But when well, you didn't finish. When I tie the string around you two, I can sit you the way you're sitting right now, or I could flip-flop you. So how many ways can you two be arranged? 2 factorial. And you 2 factorial, 2 factorial, 2 factorial. So the answer is exactly what Colin said, right there. It is exactly the same as bundling the books. Exactly the same. All right, so I'm gonna ask you one more question because kids miss this one all the time and it drives me crazy. I take 4 boys and 4 girls to the movie theater. How many ways can I seat them in a row? 8 factorial. It doesn't have anything to do with the fact that they're boys or girls, right? I'm just seating them in a row. 8 factorial. Now, if they gotta sit together or something, that's a whole different thing. Come back, 8 factorial. All right, I want to stop there. I have given you a lot of information today. So I would like you to take a couple minutes and digest some of this. Go back, highlight the big ideas, reflections, circular permutations, bundling, these main ideas, repeated elements. You've got to get all this down. Because next time we're going to switch gears, do some crazy stuff in 9-2, and then come back to all this in 9-3. Okay? You have been warned.